So let's jump straight ahead to spin coating and have a closer look at that process. The outline is here. We're going to look at what the resist is made of, and also at the pre-treatment and then the different steps in the process. So repeating again the spin coating process in a step-by-step, we want to go from our substrate to a substrate that has been coated with the resist film. And the way we do that is by taking the substrate here. Maybe I should actually send this around just in case you've never handled a substrate. I can just show you here. I have a box with some different wafers in so that you can have a look. Should be some with resist and some with patterns on it as well. So we start with the substrate, and then in most cases we need to do some kind of pre-treatment to the substrate before we start the coating process. So we just want to make sure that the resist coats nicely and also that it adheres well to the substrate afterwards. And then there is deposition of the resist. So we pour some resist on top of the substrate. Then we rotate it to coat a very thin layer. And then after that, we bake it in order to get rid of the solvent in the resist. And then we are left with a dry film on the substrate. That's the idea. So the pre-treatment before we start the coating can also be called priming or adhesion promotion. And basically what we want is that we want to make sure that the resist flows nicely on the substrate surface, and we want to make sure that the resist sticks to the surface once the process is done. So we have some different types here for different substrates. So for all the classic silicon industry ones, we use HMDS. This has a very long shelf life, so you can do it well in advance of the spin coating. Another thing we can do with the silicon is that we can strip the native oxide of the silicon using BHF. But this has to be done immediately before spin coating because the life of this treatment, the shelf life or the lifetime of it is only very short. In some cases, HMDS is not really compatible with the resist. And then what we usually have to do is that we have to dehydrate the surface just to make sure there's no moisture between the resist and the substrate. And this is again something that has to be done immediately before the spin coating. For the 3.5 materials, there is also this AP3000, which is a spin-on promoter. But it's not really something that we use a lot as a standard. It's very specific to the 3.5 materials. Okay. So going into detail with this, the way we characterize the surface before spin coating is by the contact angle to water. So what you can do in order to make sure that the substrate is ready, or at least that's how we can analyze or characterize the process, is by measuring the contact angle. And what we want is that we want the contact angle to be similar, so that the contact angle to water on the substrate is similar to what it would be on top of the resist. And this is typically in the order of 70 degrees. So that's what we are aiming for. And the way we do it is typically with the HMDS vapor priming. So this is done in a piece of equipment in the clean room. We actually also have some of our automatic spin coaters that can do it automatic as part of the process. But the idea is that we take this molecule here and expose the substrate surface to it, and then it breaks down and bonds to the surface. So we have this silicon here, which bonds very nicely to the silicon surface, and then we have some polymer-like carbohydrate end of the molecule there, which bonds very nicely to the polymer in the resist. So that's how that worked. Another way of doing it is the HF dip. So in hydrofluoric acid strips away the oxide, and then the hydrogen will passivate the dangling bonds on the surface so that we get a more hydrophobic surface. So that's what we see down here. Oh, that was. So we see here that the oxide is stripped away and that the bonds are passivated with the hydrogen. But this hydrogen will desorb, and that's why the lifetime is quite short. So the native oxide will reform within half an hour or something like that. Okay, but once we're happy with the pretreatment, we are ready to go on and actually coat the resist. And I'm just going to talk a little bit about what the resist is made up of. It's made up of 3 components. The first one is a resin. So this is the polymer itself, and it's typically solid at room temperature. And this polymer resin is mixed with a photoactive component. Now, this is something that we can add to the polymer, which will react to the UV light and bring about some kind of change in the resin. And this is the mixing of these, and is done in a solvent, which also makes the polymer fluid so that we can actually do the spin coating. And one of the things that we need for the spin coating to work, to give a specific thickness, is a specific viscosity. So the amount of solvent that we add enables us to coat the polymer at different thicknesses. Once we have a coated layer of resist on our substrate, this resist has some properties. The mechanical stability is fairly good up to around 100 degrees. So this is typically where the polymer will start to flow or to reflow, so that it changes the size or the profile of the resist of the structures. And if we go even higher, we can start to see damage of the resist and eventually burning. The chemical resistance towards acid is generally good. This is one of the things that a lot of resists are made for, is for wet etching in acids. So we generally have a good resistance towards acid, but the resistance towards base solutions will be poor, because this is basically the typical developers is a base. And also towards solvents will also generally be bad, because it basically dissolves the polymer again and takes it away. So you can see here down in the bottom a list of the UV resists that we have available in the clean room. And these are the ones that we sort of have established standard processes for. Okay, so we go into the basic principle of spin coating. The wafer is held by vacuum on a motorized chuck, and this chuck sits on the spindle of a motor, so we are able to rotate it. And then the first step is to dispense some photoresist on top of the wafer. After that, we rotate the sample to spread the photoresist evenly across the surface. And typically the speeds are in thousands of rounds per minute. And this basically means that most of the resist that we put on top is actually thrown off. And we are left with only a very thin and hopefully uniform layer on the wafer. A typical process has some steps like dispense. This can be done while the substrate is rotating or before it starts rotating. So static is when it doesn't rotate, and dynamic dispense is when the substrate is rotating. There is sometimes we need a spreading step. So this is something that typically needs to be there if we have a thick resist. So a high viscosity resist typically needs a low speed step in order to spread it evenly across the surface before we go to the high speed, which is the one where we define the thickness, the final thickness. So this is the spin-off step, high speed, typically around half a minute or 1 minute. And this is where the thickness is defined. So I just want to show you a video of this coating process. So this is one of the automatic ones. So the first thing that happens is that we get the priming in a special oven. And then the spin coating starts. You can see it starts rotating now before the dispense, so then we get a nice flow across the surface. And you can hear the acceleration towards the final speed. And then there's the baking step at the end. And you can also, so you can hear the clean room ambient, and you can also see that, that everything is yellow. So this is because we need to filter out all the blue components of the light in order not to activate the resist by the light ambient around us. We only want to expose the resist to light when we go to the actual exposure step. So all the lithography areas in the clean room will have a yellow light. Okay. During the spin coating, there is some different phases. First, of course, there's the resist dispense, and then there is the spreading of the resist as the wafer starts to accelerate. And then we have during the actual spin-off, there is a couple of different phases. There is the first one which is dominated by the flow of resist actually leaving the surface. And then at the end, when we have a uniform layer and no more flow, then the solvent in the resist will start to evaporate, and you get a thickness variation that happens due to this evaporation of the solvent. So this is a complex thing to model, which means that it's not easy to predict what thickness you'll get just by looking at the spin speed and the viscosity, because there is a lot of local phenomena like the exhaust in the in and around the spin coater and what temperature you are at and so on, which affect the film thickness. So generally what we tend to do as engineers is that we rely on some empirical measurements. So we will actually typically do a spin curve where we just test what thickness we get at different spin speeds and use that to help us get the desired film thickness. Something that can happen well, during or after the spin coating is that we can see different imperfections in the coating. The most common one is the first one here in A, like this one, where we can see what we call comets in the coating. So this is generally a particle which then leaves a tail which goes radial from the center of the substrate. So this is typically particles, and they can be on the wafer or in the resist. Could also be, if there were small bubbles in the resist, could also generate a similar effect. Another thing we might see during the spin coating is that the resist doesn't spread nicely across the surface. This is something which is typical for a high viscosity resist, where there is a low solvent content, which means that if you get some evaporation of the solvent in the surface of the dispensed resist sitting there, then it can create like a skin on top, which can be difficult to break, and you can sometimes see that it breaks off only in one direction and leaves part of the substrate uncoated. And we can also see uncoated areas like in the last picture there. So this is typically if there is not enough resist to actually uniformly coat the surface. Or another thing that can do is that if the instrument or the chuck is not centered, then you can get that the resist sort of flows off to one side and there's not enough left to coat the other side of the substrate. And another thing is that if we spin coat structured substrates, so if you already have some kind of structures that are either grown from the surface or etched into the surface, you will see comet-like defects of these substrates. And in some cases, you can actually see that, let's imagine that there is a structure right there which sort of diverts the flow of resist out so that it can leave uncoated areas behind the structures. But what we typically see is something like this one here, where we see the radial effect, shadowing effect of the structure itself. Okay. Another phenomenon that we can typically observe in the coated resist layer is the so-called edge bead. So this is something that happens on the edge of the substrate. This drawing here is supposed to represent half of a substrate, so that we are looking from the center and towards the edge. You can see that it's nice and uniform in the center, but on the edge here we have a build-up of resist, so that the thickness here is bigger. So this is what we call the edge bead, and it has to do with the surface tension of the resist, and also the way that the resist flows across the substrate. When it comes to this sudden change in the substrate as it goes over the edge of the substrate, some of these forces will actually be pulling upwards, and that generates a thicker layer right on the edge. Typically, the thickness of this is so it's very typical to see that if there is an edge bead, then it can be sort of on the order of double thickness on the edge compared to the center. And of course, it can flow out and spread out and actually cover several millimeters of the edge of the sample. It's not something that we see as a problem for the standard UV resists. There's something with the viscosity range compared to what spin speeds you are coating at, which helps. And on circular wafers, we also tend to see less of this. But if you're working on non-circular substrates, like if you're breaking chips out and continuing processing on those, it can be a very big problem. So you can see here in the picture that we see some very large edge effects there. There are things that you can do to the edge bead. It typically involves actually physically removing it afterwards with some solvent. It can be done manually or sometimes also automatically. And there is some cases where you can do things to reduce it in the way the spin process is performed, either by playing around with the spin time and also the accelerations, or by introducing some extra hardware on the spin coater that can help in this case. This is something that can typically help if you are coating a square sample. Then it's kind of like a lid that you put on top, which helps prevent a lot of turbulent flow around the sample, and also helps keep all the solvent in there so that the viscosity doesn't change during the spin coating process. After the coating, we need to do a soft bake. So this is the baking process that we do after the coating. It's called soft bake. I think it's kind of like a historic industry term for this process. So the reason why we do it is that we want to get rid of all the solvent in the resist film, because immediately after coating the resist is still wet, so it's still liquid, and we want it to be a solid film before we go on. So so we want to, of course, increase the mechanical stability of the resist, and we want actually to prevent it from sticking to the mask when we go to the next step in the exposure process. It's typically around 100 degrees, and it's 1 or 2 minutes is a typical process. Of course, if you have a thick resist, it might be several minutes, and in some cases even several hours of baking after the coating. So it's typically performed on a hot plate, and in our automatic equipment, we can actually choose between contact baking or proximity baking. So either we can put the wafer in intimate contact with the hot plate, and sometimes even hold it down with a vacuum. Or in the other case, we can keep the wafer at a distance from the hot plate. So this can have some benefits in terms of not making the hot plate dirty, and that also means that we won't get resist on the backside of our own substrate when we do the proximity baking. If we increase the soft bake temperature, we will typically see that we get a thinner film because we get more evaporation of solvent. But in cases where if we increase the temperature too much, we will see that the photosensitivity of the resist will decrease, because we can get some thermal activation of the photoactive component. And you can, at very high temperatures, so these are temperatures that the 120 degrees is something that is typical for a UV resist. We actually have resists for the stepper, and also for the E-beam, where we bake at around 200 degrees instead. So this is typical for a UV process. Is that typically, well, what can happen if you go to high temperatures there is that the resist actually starts bonding to itself, and that means you lose completely the photosensitivity, because it will not be developed at all in the developer. Okay, so here's an example of a spin curve that we have made in the clean room. So we have two different curves here for two different kinds of resist. So one is a higher viscosity that gives a higher thickness, and the other one is a low one, which gives a low thickness. So you can see here, as a function of the spin speed, the different thicknesses. And the film thickness that we get in the end depends quite strongly on the viscosity, the spin speed, and the spin time. And it can also depend quite a lot on the exhaust specific to the machine that we're using. So a high exhaust will typically take away more solvent, which means that the viscosity is increased, and that gives a thicker film in the end. It depends less on the how we do with spreading steps and what kind of accelerations we're using in the process. And provided that there is enough to begin with, it doesn't depend on how much resist is dispensed in the beginning. So when you do a manual spin coating, you can easily just deposit something by eye to be enough, and it will work every time and give you the same thickness. Even though you may put 2 milliliters one day and 3 the next, it will not give you any difference. So a spin curve like this one is only valid for a specific resist, basically, in a specific machine inside a specific clean room, because it depends on viscosity and spin time, and also how it's baked afterwards. So when you get, if you find a spin curve from somewhere else on the internet, or get it from a supplier of the resist, you cannot really expect to reproduce this 100% when you go in the clean room. You typically still need to adjust the spin speed a little bit to get the desired thickness. Such a spin curve has been modeled. So this is purely empirical stuff. You take the data and you try to fit a curve to it. But it typically turns out something like this. So we have the film thickness here, which is proportional to something that has to do with the amount of solids in the resist and the viscosity of the resist, and then inversely proportional to the spin speed used in the spin coating process. So the K is the calibration constant, and we typically combine it with all the factors that relate to the resist property, so that we get something which is specific. So we get a calibration constant which is specific to the resist on our spin coater, and using our sort of process with the spin time and also the soft bake afterwards. And for UV resists, the alpha is typically around 1/2, which means that we can reduce the thickness dependence to this one here. So you can see that we have something which is where the thickness is inversely proportional to the square root of the spin speed. And if you have a very thick resist, this alpha exponent typically approaches 1. So this is if you're using a thick SU8, for instance. And if you have a very thin resist, like what is typically used for E-beam and also for the stepper processes, the exponent can be lower than 0.5. We have there are some alternatives to spin coating out there. The most useful one is probably spray coating. So this is where instead of rotating the sample and coating the uniform layer like that, we basically turn the resist into a mist and spray it onto the surface. This has the possibility of being able to actually conformally coat even structured substrates. So even though you have large variations, large topography on top of your substrate, it is possible to coat it uniformly so that you get the same thickness everywhere. It's tricky to optimize the process, and it tends to have to be optimized for each sample. But another thing which it is very good for is the non-circular samples, because the spin coating process generally works best for samples that are circularly symmetric. And also if you have a very bulky sample, something which is heavy, that doesn't really match with a high-speed rotation, this is also a good idea. Some more exotic coating methods are mentioned here, like dip coating, where you basically have a vessel of resist and you take your sample into it and pull it out, and then you can get a coating. In this case, you would get the coating on both sides, one of the things there is that the final thickness actually depends on how fast you pull it from the bath of resist. So this is something that can be tricky to reproduce. And there's other things here, and one of them, which is that you can do a dry film lamination. So in some cases you can get the resist as a film from the supplier, and then you sort of roll it onto your surface. The ones that we have here at Danship is that we have a spray coating equipment, and the dry film roll lamination would also be possible to do here, but the rest of them require equipment that we don't have available.